All right, hopefully this isn't too dim. But anyways, a little bit on this whole unit vector thing. So let's do it in terms of acceleration, okay? So let's say something has an acceleration in the x direction of positive 5 meters per second squared, an acceleration in the y direction of positive 2 meters per second squared. So accelerating to the right and up. So in a coordinate system, right, I could draw a vector diagram of the acceleration, right? So here's the object, this dot. It's accelerating to the right at positive 5 meters per second squared and up at positive 2 meters per second squared. All right, cool. And the overall acceleration, right, would be the hypotenuse here. A would be equal to the magnitude of A would be equal to the square root of 2 squared plus 5 squared, right? The angle theta would be equal to the inverse tan of opposite over adjacent of 2 over 5. Cool. If I wanted to find out where the displacement, what the final velocity, let's say VF after 3 seconds of motion, right? So I do delta V, let's say V naught equals 0. All right, what's its final velocity going to be? What's its final position going to be? Well, I would do it in each direction, right? I'd say VFX is AX times T, VFY is AY times T. All right, so VFX would be 5 times 3, VFY would be 2 times 3, so VFX is 15, and VFY is 6. All right, positive and positive, VFX, VFY. So then we'd have to use Pythagorean's theorem and an angle to get the final speed and direction of motion, because when I report a vector, right, if I want the final acceleration vector, right, for instance, I would have to have the magnitude and the direction. If I want to report the final velocity vector, I have to have a magnitude, so I'd have to do Pythagorean's theorem, and the direction and angle, right? So I don't have a calculator here, but let's just say 15 squared. Let's say the final velocity is, I'm just going to make this up, 17 meters per second. Theta is going to be something shallow, right? Maybe 22 degrees. Just throwing these numbers out there. I didn't actually calculate it. So the final velocity is 17 meters per second at theta of 22 degrees above horizontal. Well, that gets annoying to write a velocity like that, right? So what we have invented is this idea of using unit vectors, unit vector notation. So this little arrow over the top indicates that this is a vector quantity. All right, no arrow on these ones indicate they're a scalar. These are components, right? They're just a size. I guess by putting the positive in front of that, I guess maybe I am making that a vector quantity. But typically when we report components, we don't put the vector quantity over it. We just say, what it might be. All right, so unit vectors open the door into something called linear algebra, which is a whole different subset of mathematics, all right? So in a coordinate system, what we do is we define a vector, all right? So let's make an XY coordinate system. An XY coordinate system. X and Y axis. All right, we define little vectors on this axis. So this little vector, this could be an acceleration diagram like we drew in the previous problem. This could be velocity, force, any vector quantity where the center of it represents the location of the object. All right, and that little vector we say is 1 unit in length directed along the axis. And the reason I say it's 1 unit in length is because this could be any vector quantity. This could be a force diagram. So that arrow would represent a 1 Newton force directed along the positive x-axis. And well, we give it a name. We call it I with a little hat over it. So it's a vector, and the I looks weird, right? I bent it out that way. That's because the y-axis unit vector is called J hat. So it's important you put that little tail on it for I and J so that you can tell the difference. So that little unit vector has a length of 1 located along the y-axis. All right. So what the heck does that do for me? So in that last problem, when I gave you the components, right? Turns out I could say this a little bit differently. Right? I could say the acceleration of the object is equal to plus 5 meters per second multiplied by I hat plus 2 meters per second multiplied by J hat. All right. And why do I need the I and J? Because this is a new type of notation called vector notation, and I have to have vector quantities over here. What this allows us to do is write our acceleration in terms of the components in a formula that allows us to do math to it, believe it or not. If I want to find the final velocity, let me move up here. If I want to find the final velocity, well, that's acceleration times time, right? So notice I'm putting these arrows above it, VF here, assuming plus V initial. I can write my equation of motion like this. Well, these are vector quantities. Turns out I can actually, this one, V0, there is no magnitude, so this is just 0. So the final velocity vector equals plus 5, I'm going to drop the unit here, I hat, plus 2 J hat times T. And like I said, there's rules of math that go with this. The T distributes, right? What happens while I'm telling you this, I say right like you already know it, but you don't. So the final velocity vector is the T distributes. So it's, you'd put 3 in there for the time, like in the previous example, 3 seconds. All right, so it's plus 10 I hat plus 6 J hat. And that would be the final velocity. This and this is Vx and Vy. These are the components, right? Sometimes we just, give them generic little labels like A and B and C as you learn more complex linear algebra. If this could be any number of different things in here, the components, right? I could have said AX equals 5T, and that would be, that'd go in for this. You can do calculus to this. So these vector formulas have specific rules of math that we can use. And the reason we do it is because, really the only thing you need to know is the fact that you can multiply these, you distribute to each term, all right? The reason we do this is because it's less writing. It's less writing than what we call a component form. So this is called component form of doing these calculations. This is called vector form or unit vector form. It's kind of interesting. This is a scaling factor, right? So your I hat is, again, it represents a vector 1 Newton in length. You actually don't need to put the units on these terms because the units are associated with the vector I hat and J hat. So you could actually just say it's 10 times, it's almost like saying it's plus 10 times 1 meter per second. It's almost like what it's saying there. The magnitude of the I hat vector is 1 meter per second. 10 is the scaling factor, is the component. So it's almost like saying that. But the trick is you can't add 10 and 6, right? You have to then use Pythagorean's theorem. So the magnitude of any vector, right? Magnitude of this final velocity, I would have to do square root of the terms vx squared plus vy squared. And then you could find angles as well. All right, so that's about it there. And that's it. All right.